There are a lot of both engineering and more theoretical challenges with this project. So on the engineering side, there are of course many complexities in terms of automating the manipulation of solids and understanding, again, just how to get all of these robotic components to work together. But on the more fundamental challenge side, there's questions of identifying unknown outcomes, right, and trying to respond to failures in response to uncertainty. A more concrete example of that is, let's suppose that we've asked the robotic platform to run a certain reaction, and it does so. But in analyzing the results, it needs to check if it succeeded. Has it actually made the product we want to make? Now, there are some analytical techniques we can use to check the structure, and we can try to identify whether or not the spectra that we get from some of these analytical techniques match the spectra we expect to find for that product. But maybe when we do the analysis and we do the purification and workup, we find a few other peaks in those tables. We find a few other impurities and a few other structures where we're not actually sure what's been made. The task of structural elucidation, or actually automatically identifying what those new chemical structures are, is still a very challenging research problem, right? It's, again, something that expert chemists learn how to do. It's something that expert chemists build up a skill set for, but it's not something that we can approach computationally that well yet. We need to better understand how to respond to these sort of analytical observations and dynamically choose what to do next, right? How to assess if we've been successful, or if we haven't been successful, how do we change what we're doing, right? Change the conditions or starting materials to increase our success and make the products that we're ultimately after. And it's this adaptability and responsiveness that is missing from these platforms, and that difference is how I like to describe the difference between thinking about automation and autonomy for these platforms. So autonomy has this extra component of responding to surprising events or responding to failure, whereas automation is sort of going through the motions in a prescribed manner. So my goal is to achieve that full level of autonomy where we have these closed loop systems that generate their own hypotheses, test their own hypotheses, and understand when they've been validated or falsified and know how to adjust their beliefs accordingly. So another initiative that we've become involved with recently and helps lead is an initiative called the Open Reaction Database. And so this is an initiative to create an open access platform for sharing chemical reaction data. All of our techniques and our methods, and many of our colleagues, rely on the availability of sort of well-curated, high-quality chemical reaction data. Of course, that's what a lot of machine learning tools are built on. And so we're trying to also create a sort of mindset shift in terms of how data is generated and shared, and trying to bring more of that information out into the open. So one of the ways in which our goals in automation connect to this is when we run chemical reaction screening, right, when we try to run hundreds or thousands of experiments, microliter scale, to understand the outcome, we'll get a number of successes and a number of failures, right? We might have reactions that work well, reactions that don't work well. And the status quo right now is to just publish what worked, just publish what went well. And so with this Open Reaction Database project and other initiatives we're working on, we're trying to create a more sort of open and community-driven mode of sharing data that includes those failures, right? And that includes more detail and more information than what's typically shared.